In this video, we're going to look at an example of approximating the surface area of a solid of revolution using Simpson's rule. So we're given the curve y equals x log x. We're going to rotate this curve about the x-axis on the interval from 1 to 2 for x's, and we're asked to use Simpson's rule with 10 subintervals to approximate the surface area. So since we're rotating about the x-axis, our surface area formula again is 2 pi integral from a to b of y ds. Our function is given to us as a function of x, so we're going to replace the y with x log x. And when we differentiate our x log x, using product rule, we get natural log of x plus x times 1 over x. That simplifies to 1 plus natural log. So again, here for our differential for our arc length, we'll have square root of 1 plus derivative squared dx. And the derivative here is 1 plus log x. This does not look like a formula, or excuse me, an integral we want to try to do by hand. So we'll use Simpson's rule to help us approximate. So first, we're going to calculate our delta x. That's the b minus a over n. We get delta x is 1/10. We start at 1 and go up by 1/10 until we get to 2. So our endpoints of each subinterval are 1, 1.1, 1.2, all the way up to 2. Remember, for Simpson's rule, we take delta x over 3, or 1/3 delta x. So that's where the 1/10 over 3 is coming from. We have our function values. That's what all these numbers here are, plugging in those function values. Remember, for the ones, but except for the first and the last one, we multiply by alternating coefficients. So it's 4 times f of 1.1 plus 2 times f of 1.2. The next one will be 4 times f of 1.3 all the way to 4 times f of 1.9. And then we have f of 1 and f of 2 on the ends. Putting that, calculating all of that, approximating gives us 7.248933. If you were to put this in a computer or a calculator, notice that the only thing that changes is that last decimal place there. That 6th decimal place goes from a 3 to a 4. So notice that using 10 subintervals with Simpson's rule, we get a really, really good approximation to what the value of this integral actually is.